So today we're going to be looking at something called the second derivative. And before we get onto this idea, let's just take a look at where we are so far. So this whole idea of differentiation started with the idea that if we wanted to calculate the gradient at a single point, right, gradient is defined as change, and if we want to calculate change, well, we needed 2 points. And what we did is we considered what happens as we think about the space of this change as approaching nothing. And we came up with this idea of differentiation. So over here, for instance, we might have a function that is y equal to x squared. And so when we differentiate this function, we find the gradient function, right, or the derivative. So we would get dy on dx, right? And using the power rule, we know that is 2x. So dy on dx is a function that describes the gradient. And so what I have is I've graphed it over here as dy on dx equal to 2x. It's a function just like y equal to x squared. Now I have a function dy on dx equal to 2x. It's a function that describes the gradient. Now, if we have a look at the gradient function also has a gradient. It also has a rate of change. And if we look at this function is a straight line and its gradient is constant, right? That's the definition of a straight line. So if we wanted to calculate its gradient, well, what we'd have to do is we'd have to differentiate the gradient function. So differentiation is just an operator. So we would differentiate both sides with respect to x, right? So we'd differentiate the function on the left and the right. And so what we end up with is this weird little thing called d squared y. So the d's multiply in y. And then we get dx times dx, which gives you dx squared, but we don't use the brackets, we just write it as dx squared like this. And so if I wanted to find the gradient of my gradient function, I would differentiate again. And so I can see I would just get 2 as a constant. And since it's a straight line, the gradient must be constant. So what we've calculated here, right, is what we call the first derivative. Right? It's the gradient function. It describes the gradient of the original function. And what we've just calculated here, so what d squared y on dx squared is what we call the second derivative. Right? So it's important that we look and understand the notation. Okay, so we know if we see it, we know what they're talking about. So it describes the gradient of the gradient function. And while we're not going to look at exactly why that's important now, in a few topics' time, we're going to use the second derivative to help us analyze something about all the way back, right? All the way back to the original function that we started with. So for now, let's just work on how we calculate that. And it's quite simple. Intuitively, you can see we're just differentiating the gradient function. So let's look at some notation. Right? So function can be described in 2 ways. We can have an equation y equal to something, or we can have the notation f of x equal to something. So when we differentiate, right? So differentiation, like I said, is an operation like multiplication, division, addition, right? We can differentiate an equation with respect to a certain variable. And in this case, we're differentiating x. So x is the thing we're going to use all our funny tools on. So when we differentiate y, we get dy on dx. It picks up the y. And then we can just use the power rule on this function. So 3x squared minus 14x plus 2. So this is the first derivative. Okay, now say I wanted to differentiate again. So now I'm going to differentiate. So differentiation, like I said, is just an operation. So we differentiate the whole equation. We differentiate the left, we differentiate the right. So when we differentiate the left-hand side, it picks up that d squared. And then we get dx squared, which we write like that. And so we're just going to use the power rule on this function again because it's just a sum of terms. And so we're going to get 6x minus 14. Now, another way that we can describe functions or equations is with function notation, where we would have the equation f of x or g of x or h of x or something of x. And we need to remember that when we differentiate this, its gradient equation becomes f dash x. Okay, that's the first derivative. And so it would be 3x squared minus 14x plus 2. Now, when we differentiate the gradient function and we get the second derivative, we will use the notation f double dash x. So if we see the notation double dash, that's indicating to us that we're talking about the second derivative. So it would be an equation that describes the gradient of the gradient equation. Okay, and again, like I said, that will play a big part in a few topics' time. So for now, let's just look at how we do this, right? It's quite simple. Here we've been given a function y equal to some function of x, and we've been asked to find d squared y on dx squared, which we should now recognize as being the second derivative. So we need to differentiate twice in order to get that. So I'm going to change this equation into something I can differentiate because at the moment it's not. So this x needs to come to the top and I get 5x to the minus 1. So I'm going to differentiate both sides. So when I differentiate y, it becomes dy on dx. And when I differentiate the right-hand side using the power rule, I get 3x. And then I'm going to multiply with this function by the power. So I'm going to get plus 5x. Right? Now I need to reduce the power by 1. So I'm going to get minus 2. All right, now that I've got the gradient function, dy and dx, I'm going to differentiate again. So I'm going to differentiate the left and the right. And so the left-hand side, that d gets multiplied through. We get d squared y on dx, the whole thing squared, but we write it like this, equal to, and again, just using the power rule, I'm going to get 6. So I'm going to multiply by the power. So minus 2 times 5 is minus 10. And then I'm going to reduce the power by 1. And I can tidy this up a little bit and write it back in its original form as 6 minus 10 over x cubed. And that is as difficult as it is to calculate the second derivative. So we are quite literally just taking the gradient function and we are differentiating it again to find the second derivative.